Okay, so the next bit of information we want to add to our development of understanding uniform circular motion is looking at the direction of the vectors. So once again, Newton's second law, F equals ma. Again, both of these are vector quantities. The direction of the net force and the acceleration are going to be one in the same. So again, going back to our rubber stopper lab, where we had a tension force that was pulling the rubber stopper in towards the circle, this was the direction of our net force. So it tells us that we are actually, when we do accelerate, it's not accelerating in any way the direction of motion. You're actually accelerating along the direction of the string. So along each little point along the circle, you are accelerating towards the center. And that may be conceptually a little bit difficult to visualize, but there are a lot of different ways that we can prove it. One is just using Newton's second law and telling you that the net force is in the same direction, so they have to be the same. The other way is to look at a vector model. So here's my little circle here, and let's say that my object is moving in this direction. And these are just velocity vector components of the tangential velocity. I'll use pink for this guy over here, v1 and v2. If I know that my acceleration is equal to the change in velocity over time, if I want to look at the direction of this acceleration vector, well, I can just focus on the direction of that change in velocity. So the change in velocity is going to just be v2 minus v1. And we can do a little head-to-tail addition to this. v2, and I'm going to try to draw them pretty close to scale. That would be v2. And then I want to do vector addition minus v1, so v1 is going straight down, straight up, so minus v1 would be going straight down. Kind of similarly like there, that's minus v1. And then the difference of those two is going to tell us what the centripetal acceleration is. So I'm going to use this other pink marker, reddish marker. That is going to tell me the direction of the change in velocity. So now if I take that and kind of overlap it with my circle right in the middle, I can kind of see that it is pointing towards the center. I could kind of slip it under. Can't really see that too well through there, but you can see that this acceleration vector is actually pointing to the center when I do a vector addition to it. I kind of just look at the two spaces in the middle. So for those reasons, we can see that the direction of the centripetal acceleration, you can justify your reasoning of why it goes towards the center. First, looking at Newton's second law and understanding that they both need to be in the same direction, or you can look at the vector addition of those two velocity vectors. Okay.